Can you guys online hear me okay?
Yeah, we can hear you.
Great. Oh, do either of y'all need to look at my book for the, okay. I know a lot of people don't have the books. All right, we'll give it just one more minute for anyone who wants to join a little bit late.
I don't have a book. I'll need it like tomorrow or something, I guess.
Okay, I'm gonna bring it to class with me Thursday, but someone else is already planning to use it before class. But y'all are welcome to pass it around as much as you want during class. For that homework due tomorrow, it's the optional one, right? Or is it,
Next week.
or is that next week?
And next week,
Yeah, 11's the optional one.
Okay.
Yep.
I just wanted to make sure. I was gonna
Yeah.
do it anyway, I just didn't know.
Yep, and I haven't even written it yet, so you can't do 11 yet.
That's fine. I got way too much going on this week, so I'm not. What's up next week? Shoot.
Yeah.
Yeah.
Okay, so I know I don't normally do like lecture style stuff in recitation, but there were just a couple of items that I felt like I didn't cover super well about impulse momentum that I kind of wanted to take a step back and give a little bit more intuition on. So I I have said a couple of times that there's this beautiful parallel between what I call the equations of motion. These are really like Newton and Euler's laws, but it's sum of forces equals mass times acceleration, and sum of moments equals I G alpha, like that. And they're basically almost perfect counterparts in the impulse momentum equations. So for here we have our linear impulse momentum equation, which is something like mvg1 plus sum of impulsive forces from T1 to T2 dt vg2. Okay, and notice that I'm writing these as vectors. They're both vector equations, right? I can write a version of the sum of forces equals mass times acceleration that's specific to the x-axis and then specific to the y-axis, and I can do the same thing with linear impulse and momentum. And then similarly, I have angular impulse momentum equation, which is like HO1 plus the sum T1 to T2 impulsive torques equals HO2. Okay, and again, still a vector equation. I can sum moments about the XYZ axis and I can find angular momentum about the X, Y, or Z axis. So these are like the most general way that you can do it, or write these down so that it incorporates the fact that these things all happen in all three dimensions. But when we talked equations of motion, we also talked about how things simplify when we get to the 2D case, right? So when we talk about the 2D case, we really simplify only down to forces in the X and the Y, and all our moments are just naturally all going to be about the Z axis, right? So we had sum of forces in the X equals MAGX, sum of forces in the Y equals MAGY, and sum of moments equals IG alpha. And this was moments about the Z axis. And these are scalar equations. And the same thing happens with our impulse and momentum equations. When we go to 2D and all of our, when do we even reduce to 2D for equations of motion? Like, how do we tell that it's appropriate to treat a problem as two-dimensional? Right, so the accelerations are either only in the X and the Y, or perhaps even the forces are only in the X and the Y, right? When we talk about impulse and momentum, often what we'll see is that the change in velocity is only in a plane. Okay, so if all of the changes in velocity that we care about are happening in a single plane, we can usually reduce that down and look at it from the overhead view and treat it as a planar problem. Like, we're going to do an example today where there's like a bumper car going around in a circle, right? And there are forces going, like there's a normal force and there's gravity, but the changes in velocity that we care about are only in the XY plane. And so we actually only analyze the planar view. And so what happens is we get a linear impulse momentum equation in the X. So we'll get mvg1x plus the sum of forces in the x dt integral, sorry, equals mvg2x. And notice I'm not making these vector equations anymore because they're not. Everything in this line is all in the x direction. Same for mvg1y, sum t1, t2, fy, dt, 2y. But I think the part that is probably the most confusing is recognizing that the angular impulse momentum equation reduces down to just the z-axis, and it's the exact same reason as the moments do in our sum of moments equals ig alpha. Yeah, Gia?
Is there any situation where we're gonna have to use radial transverse or normal and tangential and then translate it to these?
That's a wonderful question. In real life, yes. In this class, no. Yeah, in this class, we're just gonna stick to things that we can do with X and Y and Z. Yeah, I'll leave it at that. Okay. So then the angular impulse momentum equation then becomes, well, let's talk moments for a second. So so when we did moments for the sum of moments equation, and we say maybe we wanted to sum moments about G and we had some three-dimensional vector F. It's really hard to draw forces in 3 dimensions. What equation did we use to find the moment that this force creates about point G? We use the cross product version, right? So R as a vector cross F, where R goes from the point to the force, right? But when we were in 2D, this R cross F still holds. It absolutely holds. We can always write R cross F. But what we realized is that in 2 dimensions, as long as we use this like perpendicular distance r, the moment was always going to be about the z-axis, and it would just be this distance r times this magnitude of the force F. And it would always, always, always be about the z-axis, but then the direction of that torque, like whether it's positive or negative, we could do with right-hand rule. But recognizing that it all happens in the z-axis. But now this is scalar, we don't have to do a cross product. We don't even have to resolve F into the x component and the y component, as long as we know that perpendicular distance. Agreed? Same thing happens with angular momentum with those velocity components. So the, oops. Yes. Yeah. Okay. So when we have, let's remember for a particle, the angular momentum of a particle about some point in space, this was our bell ringer, was this, right? This was our angular momentum of that particle. When we go to the 2D case, the velocity is only going to be in the x and y direction. R is only going to be the x and y direction. And this will always resolve down into an angular momentum about the z-axis, where we can just use the distance. Instead of using a vector r, we just use the distance between the point and the particle and the speed, right? We don't have to resolve it into x and y, it's just the speed of the particle. And this is, of course, the mass. Okay, so do you see the similarities here? When we reduce to 2D, everything becomes scalar. We don't need to do a cross product anymore. And we just, as a result, everything is about the z-axis. Okay, that's important for this problem that we're about to do. I'll go ahead and tell you that it is okay for us to analyze this in the plane. So only as a 2D problem, as though we're viewing the bumper car from above. We need to treat it as a 2D problem, because if we try to write, like, so what happens is it's asking us to find the time at which the speed of the car is a certain speed. And what happens is if we try to treat it in the 3D, we end up with like this vector r is some unknown amount in the x direction plus some unknown amount in the y direction. And we get this extra relationship that we know that the total amount is 16 equals rx squared plus ry squared, right? A squared plus b squared equals, equals c squared. But the algebra gets really, really gross. And the same thing happens with our velocity vector. We'll end up with some unknown amount of velocity in the x direction plus some unknown amount of velocity in the y direction. But it really doesn't matter, because it's asking us for the speed, right? We really only ever care about the magnitude of that velocity, not which each of the individual components are. So this problem gets like, I'm sure it's possible to solve it with the 3D version of equations. It just, the math gets really nasty, and it doesn't need to be that hard. So we really need to analyze this for this class. We need to analyze this in a 2D way.
So when we see these problems, we'll only do it in the 2D way.
I don't want to promise that, but for the most part, yes. Like when we did equations of motion, you might have noticed that I really never had you do a full like 3D dynamics problem. There's an entire chapter in this book that we're not going to cover that's 3-dimensional dynamics. And you'll even notice in the chapter headings, it says, I think, like planar kinetics of a rigid body. And And that's on purpose because these things you have to use vector algebra to do them at the 3D way. And we just don't cover that in this class. So yeah, for the most part, you're going to be able to analyze these more difficult impulse momentum problems in the plane. So you'll see that through the problems we do today. Okay, questions? Did that help at all? All right, I'm gonna leave you here to make an attempt at this.
I have a question.
Yes, Samuel.
It says the engine supplies a traction force. Does that mean it's assisting the direction of motion or is it resistance? Like friction.
You can assume that what they're describing is a force pushing the bumper car.
Okay.
Yep, just like it's drawn.
The moment being applied as well as a force on the car.
Yes. Yep.
It's positive moment, right?
Depends on how you set your coordinate system. So here's the free body diagram that I drew. I said, let's call the center point A just for the heck of it. And we'll pretend that this is just a particle on a massless rod. We'll have force equal to 15T. We'll have this M equal 30T squared. And I'm going to set X here, Y here, meaning that Z is out of the page positive, which means that this moment is positive.
Okay.
Make
Yeah,
sense?
it was just hard to see the blue arrow, like which way.
Oh, yeah.
Yeah.
Sorry. Yeah, absolutely. But actually, there's also some reaction forces here, AX and AY. All right, Giovanni, where are you stuck?
I got 3.33.
Oh, there you go. You're correct. So what equation did you think was going to be useful?
MV plus the integral of forces for T equals MV2.
Okay, so you did,
I just divided the moment by the 4 and then just use that.
so you did linear momentum?
Yeah.
That's interesting. Micah, what did you do?
I did as two separate components. I did the force and then I did the linear and then the angular, but then converted angular to linear.
Interesting.
Okay. Yeah, if you're given the length, you can always simplify the forces. That's just always what I've been doing, even at the homework.
Okay, fine. I'll do it a slightly different way, just to give you some exposure.
What was the answer?
3.33.
I got 4.4. I just don't know how to use a calculator, I guess.
Oops. Okay, I did the principle of angular impulse and momentum about point A. So I have H A Z1 plus some integral T1 T2 M A Z dt equals H A Z2. Okay, so here we're in the 2D. So we have R M V1 plus integral from 0 to 5 of that couple, which is positive, 30t squared. And then that force creates a positive couple as well. So plus 15t times its moment arm of 4 meters, I believe. Is that right? dt equals rm v2. And the r is the distance between the point and the particle, which here is that same moment arm of 4. We're starting from rest, so initial velocity is 0. So we should just have to do this integral. So
I thought the
30.
moment was r squared. Did I miss it?
Say
I thought it
again.
was 30 r squared for the moment.
30t squared.
Can I look at it on the equation? I must have just completely missaw it. I did just completely missee it. Okay. I'm tired.
All good. Okay, so 30t cubed over 3 plus, is that 60? Yeah, 60 t squared over 2 evaluated from 0 to 5 equals, what's my mass? 150. Okay. So I won't go through all of it, but absolutely the correct answer is 3.33 repeating meters per second. Okay, so there's a lot of different ways to do this. I'm not surprised at all. However, how many equations did you have to use? You just did
1.
In
I
the-
just divided the moment instead of multiplying the force. And since it simplifies for 2D, then it's
Yeah,
just the force.
but the linear, oh, but did you end up with an I hat equation and a J hat equation?
No. I did the integral from 0 to 5 of 7.5 t squared plus 15t equals 150 times the velocity. And then
So it was
divide
just in the J hat direction?
Yes, it's like if I'm looking at it from the top.
But what about this reaction AX and AY?
Well, I'm only looking at the car.
But
Distance
the,
across the,
but these are applied to the car through the massless beam.
that's how the moment is carried, right?
I mean, it clearly works out, but the reason that doing the angular impulse and momentum about point A is the right way to go is because you're taking moments about A, so those A reactions don't come into it.
Mhm.
But if you're doing linear impulse momentum in either the X or the Y, you really should take into account those AX and AY reactions.
Okay,
But maybe it,
but isn't it because it's fixed there, like, that's pinned there, so it would just rotate along with it?
a pin still has force reactions. It just doesn't have coupled reactions. But it may be that for some reason those reactions are actually zero in this problem. And maybe that's why it was okay. But it's very similar to moments in that if there are forces you don't know and you don't want to show up, you can take the moment about that point and they kind of don't come in.
If you're given, like, let's say for instance, you're given AX or AY, can you still sum about A and get
Mhm.
okay.
Okay, moving on. Well, I have 3 problems for us for today. All right. This one should be a pretty simple one for our first rigid body impulse momentum. So the 2 tugboats each exert a constant force F on the boat such that these forces are always directed perpendicular to the boat's center line. If the boat has a mass M and a radius of gyration kg about its center of mass G, so let's keep in mind kg equals square root I g over m. Determine the angular velocity of the boat as a function of time. The boat is originally at rest. One thing I don't like about this problem is they really needed to show you that the center of mass of the boat is directly in the middle.
What's the value? Like, what's the distance between each boat? We're just assuming it's like half.
It's D. So from F to G is 1/2 D on either side.
Would it be possible for you to zoom in just a little bit?
Yes. Let me just make the picture bigger.
Oh, thanks.
bottom force, are we negative? Are we just assuming don't worry about it?
It's just forced in the direction shown.
Okay.
Okay, so I did angular impulse momentum about G. And so since G is the center of mass of the body, we get I G omega 1 plus rho T1 T2 mg dt equals I G omega 2. IG is just going to be kg squared m. But we start out at a omega equals 0, so really that term goes to 0. All right, moments, we're going to have F times 1/2 d in the minus z direction. I'm going to write this as 0 to t, so we keep t in the equation. So minus F times 1/2 d. And then we're going to have another minus F times 1/2 d equals kg squared m omega 2. All right, so this should just be minus F dt equals kg squared m omega 2. So omega 2 is minus F d over kg squared m. And why is it negative? It tells us the direction. So it's not wrapping positively about the x-axis, it's wrapping or about the z-axis, it's wrapping negatively. So it tells us that this angular velocity created is clockwise. So we can either write that as k hat or f d over kg squared m clockwise.
Where did the T go?
What?
Where did the T go?
Sorry. It disappeared magically. No magic in this class. Yeah, I'm sorry.
Sure.
And the positive negative is just applied using the right hand rule.
Correct. Yeah.
Okay.
But it's set by how I set my coordinate system, right? So X, Y, Z is coming out of the page based on the way that I set X, Y. So the positive K direction is out of the page, which means that a counterclockwise rotation is positive.
Thank you.
Yep. Questions?
Could you solve this problem another way?
Very likely. How would you like to do it, Giovanni?
No, we don't have to do it. It's just I forgot about the equation that you used. So I was gonna integrate the sum of the moments. You put IG alpha. And I was just gonna integrate the alpha. I think it would get the same answer.
It probably does because these forces are constant. When the forces are not constant, if you know the function of the force as a function of time, you can still probably integrate it. But if the forces are non-constant and you don't know what the function is with respect to time, it's very difficult to
Yeah.
solve that. Yep. Okay. Last problem. This is probably the most involved one, I believe. Yeah. It's a little more involved, mostly because we have to figure out what force certain forces are in the X and the Y and then do angular momentum. Um, but I'll let you take a stab at it. Do I need to make anything bigger? Okay. And yes, Giovanni, there are absolutely multiple ways to do this one.
Okay, that's Dude, I hate that. It's pin joints at both A and B.
Correct. You can also assume that I know it says cylinder, but you can use the moment of inertia for a thin disk, which is 1/2 mr squared.
Why did you write two FABs?
Yeah, because it says it's asking what is the force
two
developed. Yeah. You want me to continue that thought?
No, I'm just.
Oh, okay. You're
No,
looking
making sure
behind me.
I have-
Sorry.
Sorry, no, I should.
It's sometimes hard to tell whether you're looking at the screen or directly in my eyes.
This was 490.
Yep.
So, sorry, AB, is
Yep.
there no Y direction? Oh, that's AB. You showed it for
There is not. AB is safe to assume it's massless because we're not given a mass. And therefore it's a two force member. There's only forces applied at A and B, which tells us that forces being applied by this member AB can either only be tension, tension or compression along that line that connects A and B. So it's only in the X direction.
Can you just ignore it anyway, because it's about the center of axis of about the like. Origin,
Yeah, it's not going to show up in the moment equation. Yeah. So if I really cared what that force was, I could have done like the sum of forces in the X equals 0 as well, because it's not going to accelerate, but we really don't need it to find what we're being asked for.
Don't you need it for the second half of the problem?
Oh, yeah. Okay.
Oh.
Yeah, I forgot the second half. Okay, so sum of forces in the X equals 0. So force of friction minus 2FAB equals 0. Which is 0.2 times 490.5 minus 2.
is it 30?
Yep. Would be it for T2.
1.53.
Very good. Okay, so some alternative ways that this could have been done. We could have actually used our linear impulse momentum in the y direction to find n. We could have used linear impulse momentum in the x direction to find FAB. But I didn't because I don't have to. I feel certain there's probably a couple of different ways we could have done this last part, but I think this is probably the most direct. Any questions? Questions?
What did your integral look like?
It was the integral from 0 to T2 of mu k n.
Force was-
Friction force is mu k n. So 0.2 times 490.5 times 0.2 again.
Why should I do 0.2 twice?
Because it's the force of friction times the moment arm.
Oh,
So the force of friction has a 0.2 in it because it's the coefficient of friction.
And then even though the values go to be negative, it doesn't matter.
Which value?
Your seconds is.
Oh, sorry. This is supposed to be negative.
Okay, that's where I was getting confused.
Yep, yeah, because it tells us that like we set our x and y so that z is positive up, but
So it's a
the
negative.
initial velocity is in the negative z direction. So that should have been a negative. I apologize.
Alright, that makes sense.
If you would have done the as clockwise as positive, then you would just have to have the moment in the integral be negative.
Yep. That would be equivalent to that coordinate system. Yep. All right, questions? Comments? Concerns? Okay, let me know if anything comes up. Thanks, everybody.
Thank you, Dr. Higgins.
You're welcome.
Thank you, Dr. Higgins.
You're welcome.
Not quite to the scale. All of them.